Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering, Yeola. In the previous lecture, we discussed about open loop and closed loop control systems. Beyond this, we are seeing now the transfer function and mathematical modeling of a control system. In that, first part is control systems and complex of a single loop systems. Here, if we are going to discuss about input and output of the system, then it will be considered as a single forward path. Beyond this, a four transfer function in the forward path will be noted as this one is G, that is G1, second one is G2, then G3, then G4, and some reverse path will be considered as H1, H2, H3. In this diagram, the R of S will be considered as input of the control system and C of S will be noted as output of the system, and each and every block in between this input and output system will be considered as a control system. So moving towards the transfer function, this control system basically deals with representing the physical devices as mathematical equations and analyzing them. The distinction between physical system and models is a fundamental in engineering and in control system models. Hence, this physical system is a device or a collection of devices existing in the real world, while a system is a model of a physical system. See in this diagram, basically it consists of a block with at least one input terminal and at least one output terminal. Here, R of X will be considered as input and C of S will be considered as an output. In case of this R of S, X of S and C of S in place of Y of S will be taken as. This S will represent the system domain, means it is a frequency domain. When it is in a normal function form, then we will call it as a R of t and C of t. T indicates time domain of the function. When we take any Laplace of this system, this R of t will get converted automatically into R of S, and this C of t will get automatically converted into C of S. This choice of the model representing a physical system completely depends on complexity of the mathematical modeling used, and it is useless to choose a model that closely resembles the physical system but cannot be analyzed by using existing mathematical models. And similarly, it is futile to have a model but can be analyzed easily but does not represent the physical system correctly. The system that we use in this can be described by ordinary linear differential equation. That linear differential equation we are discussing in the block diagram reduction techniques, and this equation with the constant real coefficient. Here X of S means R of S is the input signal as said earlier, and Y of t is the input signal, that is C of S, and some A1 and B1 are the real constants, and here the value of n is always equals to or greater than m, and such a system are called as linear time invariant system. Here, a linear system is one that satisfies the superposition principle and additive and homogeneity property. A time invariant system is one whose input and output characteristics does not change with the time. that is the time output relationship. Basically, these signals and systems, if we want to learn about the LTI means linear transfer or linear inverse transfer system. And for this purpose, let us simplify that we shall deal only with the systems that are linearly time invariant. Now we are moving towards the definition of the control system. Basically, this transfer function gives us the relationship between the input and output, and hence it describes the complete control system. Here the definition of this transfer function, as it is defined as the ratio of Laplace transform of the output to the Laplace transform of the input under the assumption that initial conditions are zero. Here, whenever we are going to take C of S as an output and R of S as an input, let us consider the initial conditions are always zero. Okay, so before we are moving towards the transfer function, as per our definition, Laplace transform of output, that is C of S, upon Laplace transform of the input, that is R of S, when the initial conditions are considered to be equals to 0. To derive this expression, firstly we know that this transfer function is equals to the ratio of Laplace transform of output to the Laplace transform of input, and this Laplace transform is equals to, basically we consider this Laplace transform as G of S. G means gain, so is equals to, in numerator we have to write Laplace transform of output, that is C of t, and C of t indicates the time domain function, divided by, or write down in a numerical denominator, R of t, or Laplace transform of R of t, means input in time domain function. So we can easily find out the transfer function of any system. See this block diagram. In this block diagram, as we discussed previously, G1, G2, G3 and G4 is the forward path, then H1 is the feedback path, H2 is also feedback, and H3 is also feedback. While doing this, we have to note that these 2 of H transfer function in the flow graph have negative sign. So whenever we are writing the equation, consider this H1 and H2 will be equals to negative sides. This is necessary since the summing nodes do not have any signs associated with them as in the block diagram. This is all about the transfer function of the system. Now, whenever we are moving towards the poles and zeros of the transfer function, the transfer function, let us move a little further. If the transfer function is noted as G of S is equals to V0, that is output of S upon input of S. What is input? Input is R of S, means gain G of S is equals to C of S upon R of S, where C of S is identified as the Laplace transform of output to the R of S, means Laplace transform of input, and hence both the C of S and R of S are polynomial, and this polynomial can be simply written as G of S is always equals to, that is gain is always equals to Bm into Sm plus Bm minus 1 into Sm minus 1 and so on, divided by An into Sn plus An minus 1 into Sn minus 1 and so on. So these poles of this transfer function are basically just value of the Laplace transform variable S, and that causes the transfer function to become infinite. Similarly, these poles can be easily found out by equating the denominator of a transfer function. I am repeating, the poles of the transfer function can be found out by equating the denominator of the transfer function is equals to 0 whenever any transfer function denominator can be equated with 0, then we got the value of s, and that particular value of s, whatever it may be, a positive or negative, is considered as a poles. And similarly, to find out the zeros, the same process can be done, but we have to consider the numerator of the transfer function is equals to 0. At the same time, also the values of s we got, sometimes it may be single value or double value. All these values are known as the zeros of the transfer function. So these poles and zeros are basically we need for plotting this block diagram. And before moving towards the flow graph, we have to study the signal flow graph of a particular transfer function.